Let us continue with the second lecture of this course, still an introductory lecture. In the last lecture, I talked about single input, single output control, talked about what servo control means, what regulatory control means and so on. And I had made the point that most of the time we study single input, single output control. However, real processes are really multiple input, multiple output. This is actually a picture that I had shown at the end of the class last time, where I said if you have a plant like this, there are likely to be multiple inputs that you could manipulate to control multiple outputs which are of interest from a profitability or safety or any other point of view that you might have. So, the question is, if we learn CISO control quite a bit, how does that translate to this MIMO control is an interesting question that we would like to answer. So, let us take a top down view of process control. As I mentioned in the previous lecture, the overall goal typically in running a process plant is maximization of profit, obviously subject to all safety and regulatory standards. Let us consider a chemical process such as the one I showed in the previous picture, just for a mental image of what we are talking about here. It could be any other plant. If you want to compute the overall profit that you are likely to make from this plant, so you can write it as following. It is the income from selling all the products produced minus the cost of raw materials that are used to produce these products and also utilities that we use. So, for example, we might need electricity to run the plant, we might need heating, cooling and so on. So, if you subtract all of those costs out, then that will give you the profit that you are going to make. Mathematically, you could write this profit as a function p, which is a function of several process variables that might participate in this profit function. Now, the idea is really to figure out how to maintain these values at certain values, and of course, what those values are supposed to be, so that I maximize my profit. There are two approaches to doing this. One is to actually mathematically formulate this profit function as a function of several process variables, and then say if these process variables were to take certain values, then this profit function is maximized. However, because most processes are rather complex and the first principles modeling of the processes themselves become very complex, usually this is not how people identify the values for these process variables. In general, what you do is you might have done subsystem testing. So, for example, if a reactor is a part of a big process, you might know that the optimal temperature at which I should run this reactor is this. So, you would use that value instead of doing a composite profit function and so on. So, from small subsystem testing or lab testing, you have a decent idea of what values you want these variables to take, and of course, you would use your process insight to come up with these values and also look at similar systems and what ranges of these variable values do they operate and so on to get you an idea of what numbers make sense. So, this is what I have written here as heuristic knowledge. This is what is done in most process plants to come up with values for these variables that will maximize the profit. Now, once you have this profit optimized at these values, so that basically means that you have to maintain these variables at these values. So, in some sense you have to control these variables to take these values. The problem of control variable selection, it is the one where if you have a process, you are going to say how many control loops do I need? Do I need 10 control loops, 15 control loops, 20 control loops? That is a question that we are trying to answer. So, the logic is that I need to keep all of these variables at some set values. So, out of those I might pick the ones that are most sensitive and then say okay, those are the ones that I am going to control at those values. So, that is one simple idea that you could use, or you could say I am going to find a linear combination of these variables and then maintain them at certain values and so on. So, there are several heuristic ideas that one could use to figure out what variables that you want to control. Of course, outside of this there are certain variables that are related to safety which you will surely want to control. For example, temperatures and pressures, when temperatures and pressures go high in a process, you would really want to control those, because the reactor vessel will have metallurgical limits beyond a certain temperature, it might crack, melt and so on, and beyond a certain pressure these vessels might burst. So, those are standard safety critical variables that you need to control. What we are talking about here is outside of those, the variables that are things that you want to control, so that you run your process optimally. So, you would pick in some sense a subset of these variables as control variables. So, when we think about the process picture that I showed you, and you are trying to think about how to control this process, the first step of what are the variables that I need to control is done in this manner. You could do all of this very mathematically in very sophisticated fashion, but in most cases in real industrial practice, it is done more from prior knowledge and insight about the process. Okay. So, at this point, let us say I have figured out how many variables that I want to control. Now, as we talked about in the CISO control, when we have variables that we want to control, we need to figure out variables that we should manipulate. So, I have to find out what variables can I manipulate in the process. So, manipulation automatically means I should have some mechanism of changing the value of these variables. So, for example, if I have a pipe and there is a flow through a pipe, and I want to manipulate the flow to take any value I want, then basically what I need to do is I have to put in a valve, what we call as a control valve, an actuator, which I can manipulate to make the flow be anything that I want. So, I have to figure out variables such as this. Do I want to manipulate flows? Do I want to manipulate some pressure so that I can control something else and so on. So, I need to find enough of these manipulated variables so that I can control the variables of interest. So, in general, heuristically, the notion of selection of these manipulated variables goes like this. Of course, these variables should have a strong impact on the control variable. So, if I have a manipulated variable which I change and nothing happens to any of the control variable, then this manipulated variable is not useful. So, I want to find manipulated variables which have very large impact on the control variables. Now, the second thing is there should be enough of them. So, if I have 10 variables that I want to control at certain values, and if I use just one manipulated variable, it is not going to work most of the times. So, I need to have enough of them, and really if you think about control, there is a notion of moving variability from one variable to another. What I mean by this is the following: supposing you take this control variable C1, we want it to maintain a value here, but because of disturbances, let us say it is varying like this. So, basically what we want to do is we want to go from here to a situation where it is flat. That means I want to reduce the amount of variability in this control variable, and as they say there is no free lunch. If you want to reduce the variability here, that variability has to be moved to somewhere else. So, the essence of control is basically moving this variability to a manipulated variable, so that that manipulated variable moves, but it keeps this to be a consistent value. So, in some sense I am moving the variability from a control variable to a manipulated variable. Clearly, I am trying to move the variability because this is not good for me from an economic point of view. So, if I find an equivalent variable where if there is variability, it is not really good for me, then there is no point in doing control. So, the idea is to move variability from variables of serious interest from a profitability viewpoint to variables which can change, will not have a big economic impact, but these changes will make sure that the control variable is tightly controlled. So, the economics also plays an important part. So, to summarize, when we look at a process plant such as the one I showed, then you have to do a careful selection of control variables and a careful selection of manipulated variables. In much more advanced control classes or advanced control techniques, one can talk about how to do this very systematically, mathematically, but in general you might understand this more heuristically and then say the control variables are the important ones from a profitability viewpoint, and the manipulated variables are the ones that are enough for me to manipulate so that the control variables stay at their desired value. And in fact, most industrial processes, the choice is usually through some heuristic like this. Now that we have, let us assume, chosen the control variables and manipulated variables, and notice in the block diagrams that we have been showing. So, if I have a process block, okay. So, what we say is that if there are, let us say, several manipulated variables, in this case I am calling them M1 to Mn, and let us say there are several control variables. If I draw a block diagram like this, what this means is that if I manipulate all of these variables through the process, whatever the connections are, the physical connections, the control variables are going to take certain values. So, this is a process model where by manipulating these variables I can change the control variable values, and only because by manipulating these variables I can change these control variable values, I can actually control these variables to whatever desired values that I want them to take. However, from a controller viewpoint, the idea is to say, okay, if these are certain variables and they have to take certain values, how should I choose the manipulated variable? So, in some sense the controller is the inverse of the process. In the process, the manipulated variables dictate what the output is, and in the controller the outputs dictate what the manipulated variable values are. So, if I have so many control variables, then controller is some mathematical calculation which will see the values of these control variables, check them against a desired value for them, the set points, and then decide the manipulated variables have to be set at these values. And once these manipulated variables are set at those values, because they are physically connected through this process, they are going to change the control variable values, and then again you will check whether these control variable values are close to their desired values. If yes, then no need for any more manipulation. If not, you keep manipulating till the control variables go close to their desired values. So, that is the basic idea of control. So, if you think about a truly multivariable control, then what we will say is there is a controller which gets as its input all the control variable values, and the controller has to decide all the manipulated variables at the same time, right. So, if you truly think of this as a multivariate problem, you should solve this at one shot. However, in the previous lecture you would have seen that we have single input, single output, right. So, one manipulated variable for one control variable. So, one might ask this question and then say, look, I want to do this multivariable control, however, I want to only implement single input, single output control, okay. How do I do that? So, immediately you will notice that if I have to break this down into multiple single input, single output controllers, then I have to pair the control variable to a manipulated variable. So, I might say C1 is paired with M1, C2 is paired with M2, and Cn is paired with Mn, right. So, I might have to figure out for every control variable what is the corresponding manipulated variable, so that I can pair those and then break them into single input, single output controllers. Now, in real industrial practice, as I said before, many of the processes use this kind of pairing to come up with multiple single input, single output controllers, so that the process can actually be controlled very effectively. If you ask why would someone want to do this, the reasons are the following. Number one, as you might imagine, if I had, let us say, 100 control variables, 100 manipulated variables, thinking about all of them and looking at a control which has multiple control variables and multiple manipulated variables might become very complex, and it might not be easy to understand how to design this controller. So, the analysis and design of multivariable controllers might become too complex for standard application in many industries. The second and more important reason is, supposing I were to do this multivariable controller, that is multiple variables are being controlled by multiple manipulated variables. Let us say the controller fails. All engineering systems have certain reliability, all of them are prone to failures. So, if the control system fails, then at one shot you lose control of hundreds of variables. So, that is something that people worry about. So, you do not want to do that. Instead, if I had broken this problem into let us say 50 or 100 single input single output control systems, even if one of the CISO controllers fail, all the others are working. So, from a reliability viewpoint, it makes lot more sense to think about the problem like this, though breaking a multivariate controller into single input single output controllers could give you a suboptimal solution. And the third reason is, whatever is the optimality that is lost because I am breaking down a multivariate problem into single input single output problem, those can be somehow compensated for by using very simple advanced concepts such as cascade control, ratio control, feed forward control and so on. These are what are called traditional advanced control ideas, and these can be easily incorporated into CISO controller framework. So, it is a very simple block that you can add to existing controllers. So, we avoid complexity, we maintain reliability, and we compensate for suboptimality through very simple techniques. So, multiple single input single output controllers are actually very effective even for real multivariable processes. So, let us kind of think about how that large problem is broken down into smaller problems. The reason why I am showing this here is to give you an idea of how for realistic real industrial problems we start from an overall concept of control which is inherently multivariable, and then we break that down into single input single output controllers and think about single input single output controllers for the next 15-20 lectures. So, I just want you to understand that while we are doing the CISO controller, it is not as if we are not solving the original problem. We are still solving the original problem through clever means is something that you can think about. So, let us take this process for example. So, here much like how I have shown in the previous pictures. So, this process has let us say 2 manipulated variables and the output 2 control variables. So, this is a process where the manipulated variables are the input and the control variables are the output. And as I mentioned before, a controller is an inverse of the process. So, here I have the controller values as the input and this gives me the manipulated variables as the output. Now, if I were to do this truly in a multivariate fashion, I should get these values and then do some computation so that M1 and M2 are calculated together for these 2 values. But as we have been saying, what we are going to do is we are going to break this down into single input single output controllers. So, when we do that, the block diagram may look like this. Let me trace one thing here to give you an idea of what is happening. So, let us say I pair M1 and C1, then this loop 1 of this process, this block basically says whenever there is a change in M1, how does C1 change. Okay. So, this block has M1 as input and C1 as output. So, this C1 goes here, and because this process is multivariate, the changes in M1 is not the only thing that is affecting C1. The changes in the other manipulated variable M2 could also affect C1. So, this is what we have, and because of linearity here we can say the total change in C1 is because of changes in M1 which is acting to actually control C1, and also changes in M2 which is acting to control C2, but because it is multivariate, whenever that changes there is going to be effect on C1 also. Now, this combined effect is shown as C1 here, and that is compared against a set point to generate an error. So, remember this is an error only for C1, and that error goes through the CISO controller which has only one single input, which is the error between C1 and its desired value, and it decides what M1 is. Now, a similar situation occurs for the other loop. I have loop 2, you can see that M2 affects C2, and any change in M1 which is because I want to control C1, it will also have an effect on C2. So, these 2 are added, and then I have C2 value here which is compared against its set point, and that error goes into the second controller which decides what M2 will be. So, when I go from here to here, I have not lost anything at all, because though I am thinking about this as CISO controllers, the effect of the other manipulated variable I am still showing in this picture, and the effect of the other manipulated variable comes in as a disturbance to the individual seesaw loops. So, that is how you want to think about this seesaw control. So, when we finally look at this, what happens is you can simplify this into this block diagram, where you have loop for process 1. So, which is basically M1 coming in, and the effect of M1 C1 because of the effect of M1 here. And now I have broken down that picture into two different pictures. So, I am going to say the effect of M2, which is other manipulated variable, you might want to think of that as a disturbance that changes the value of the control variable C1, and there might be other disturbances in the process which also change the value of C1. Nonetheless, this C here, C1 here, is a combined effect of what M1 has on C1, which is directly the manipulated variable that is used to control this, and the unavoidable effects of M2, which is trying to control C2 on C1, and the unavoidable effects of disturbances which anyway we have no control over. So, you could see that I have now got a single input single output loop for C1 and M1, where the effect of M2 and D are counted as disturbances. Now, a further simplification is, because it is linear, I can add all of this and say this is one disturbance, and then I have disturbance model. Now, this looks like your standard single input single output controller. There will be a corresponding single input single output feedback block for C2 M2 pair also. Now, how do I analyze control loop like this for a multivariate process? What you typically do is, this disturbance is something that is unknown. So, once you design the controller, which you will study or learn as we go through this course, you will check how well this control loop works for all kinds of disturbances, and you will check how well this control loop works for all kind of disturbances, because you know that there are natural disturbances that come from the environment, and also the disturbances that come out because the other loop is trying to control for C2, right. So, by looking at various disturbance models here and then ensuring that this loop works even when there are several different types of disturbances, we convince ourselves that the single input single output loops will do quite well for the multivariate process. So, that is the basic idea of how we break down a multivariable scheme into multiple single input single output schemes. The critical idea here is that you should test these schemes quite well by looking at several disturbance models to see that whatever interaction effects we have lost, we still analyze them and then see whether the loop is going to perform well even in the presence of such interaction effects. So, I hope this gives you an idea how a multivariable control problem is broken down into several seesaw control problems. Though we lose optimality, I hope I have convinced you by looking at it in this fashion. When we test these single input single output control loops, we do have a notion of the fact that this testing is being done for an inherently multivariate process, and the lost optimality could be made up by simple, very traditional advanced control as they call it, and all that you learn in seesaw control is really in some sense very useful for real process control also, and in fact this is borne out by the fact that about 90% of all control loops in industrial processes are really seesaw loops, and they still perform very well. So, with this I will stop this lecture, and I will see you again in the next lecture with more concepts in terms of feedback control, nomenclature, different control structures and so on. Thank you.